Hello, in this lecture we'll find out the area of the circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have this circle. In addition, you know that side AB of the quadrilateral is equal to 2 units in its length, side BC equals to 8 units, and side DC also equals to 8 units. This angle DCB equals to 90 degrees. This angle ABC also equals to 90 degrees. Our mission is to find out the area of this circle. So first of all we'll do construction. We'll extend side BA and side CB of the quadrilateral until they touch each other. We define the touching point of the two sides, SM, this point, and here we actually extended side CB of the quadrilateral by a straight line. CB is one side of the quadrilateral, it is absolutely a straight line. When we extended the straight line CB by a straight line, the result is CM. And when you extend the straight line by a straight line, the result must be a straight line. So CM must be a straight line. So if we focus on the upper side of the straight line CM at point B here, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees. So the missing angle here must be equal to 90 degrees. Okay. So in the right triangle A and B, we define this angle as theta. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. We focus on the big right triangle MDC. On this big right triangle, the big right triangle MDC, we have this angle that is equal to theta. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Exactly like this angle. Okay. In the next step, we'll prove that the big right triangle MDC is similar to the small triangle NAB. So write it down. Triangle MDC, the big right triangle, is similar to the small right triangle NAB. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So This is angle DCP in the big triangle. That is equal to this angle in the small triangle. This is actual angle ABM. Repeat again. Angle DCP in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees. Therefore, they are equal to each other. In addition, this is angle theta. That is a common angle. It belongs to both triangles. So angle theta equals to itself. You can call or you can define angle theta. You can call to angle theta two different names. Angle theta can be called angle DMC. When we relate to angle theta, as it belongs to the big triangle, angle DMC. And it is equal to angle theta itself. You can call to angle theta angle MAB. Angle AMB. When we relate to angle theta, as it belongs to the small right triangle. Repeat again. Angle theta is angle DMC. You can call to angle theta also angle AMB. So angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MDC, the big triangle. And it is equal to this angle, that is actually angle MAB in the small triangle. Repeat again. Angle MDC equals to angle MAB. Angle MDC, the big triangle, equals to angle MAB, the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore we proved that the big triangle VCM is similar to the small triangle MAB according to angle similarity rule. So I write it down, and triangle DCM, the big triangle, is similar. This is the sign of similar to the right small triangle MAB. According to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all the angles in one triangle are correspondingly equal to all the angles of another triangle, then the two triangles are similar to each other according to angle similarity rule, exactly as we proved about those two right triangles. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that MC, the big triangle, or MB, the small triangle, equals to DC, the big triangle, over AB in the small triangle. I repeat again. MC over MB equals to DC over AB. What is the length of side MC? From the drawing it is very easy to see that MC equals to MB plus BC. That is to say, MC equals to MB plus BC. BC is 8, so in total MC equals to MB plus 8. Repeat again, MC equals to MB plus 8 over MB is equal to DC is 8 and AB is 2. So DC over AB is 8 over 2. 8 over 2 is 4. So we found out that MB plus 8 over MB equals to 4. We multiply this equation by MB. And we get that MB plus 8 equals to 4MB. We subtract MB from this equation. And we get that 8 equals to 4MB minus MB is 3MB. So 8 equals to 3MB. We divide this equation by 3. And finally we get that MB equals to 8 over 3 units. We can write down here that the original drawing, that MB this line segment MB equals to 8 over 3 units. In the next step, we implement the Pythagoras theorem on the right triangle MAB. Here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AMB is AM, therefore the square of the hypotenuse is AM squared. And this is equal to AB squared plus MB squared. Repeat again. According to the Pythagoras theorem, in the right triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, so AB squared is 2 squared, that is 4, plus MB squared. AB is 8 over 4, therefore MB squared is 8 over 4 squared, 8 over 3 squared. MB is 8 over 3, so MB squared is 8 over 3 squared. So we found out that AM squared, equals to 4 plus 8 over 3 squared equals to 8 squared, that is 64, over 3 squared, that is 9. Here we multiply this equation, we multiply 4 by 9 and then we will divide it by 9 in order to have a common factor with 64 over 9. And we get that AM squared equals to 4 times 9 is 36 plus 64 over 9. 36 plus 64 it is 100 over 9. So AM squared, we take a root out of this equation, AM squared equals to 100 over 9. We take a root out of this equation and finally we get that AM equals to the square root of 100 over 9. The square root of 100 is 10, and the square root of 9 is 3. So I conclude found out that AM, the square root of 9 is 3, so it is found out that AM equals to 10 over 3 units. AM, the potential AM equals to 10 over 3 units in its leg. In the next step, I present to you a new rule number 1, and we will implement rule number 1 in our drawing. So according to rule number 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent AB is tangent to the circle at point M. We have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with the circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. We can implement rule number 1 in our drawing. We define the center of this circle, this point as O. AB is tangent to the circle at this point. We define the point of tendency as M, and join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself. Therefore, OM is the radius of the circle that we define as X. We have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to rule number 1. BC is tangent to this circle at this point. We define the point of tendency as N. We join points O and N together by a straight line. ON is the radius of the circle that we defined as X. We have the radius ON that is drawn to point N, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. So we'll focus on quadrilateral MONB. In this quadrilateral we have 1, 2, 3 rectangles. The sum of 3 rectangles is 90 times 3 is 270 degrees, plus the fourth angle. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here, the missing angle must be equal to 90 degrees. 270 degrees plus 90 degrees, it is 360 degrees, exactly according to the rule that I mentioned. Okay. In the next step, we'll do a construction. We'll draw perpendicular on BC in such a way that it will be also tangent to the circle. So this is perpendicular, that is to say this angle is perpendicular to BC, that is to say this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point between the perpendicular and BC is K. We define the point of tendency of the perpendicular with the circle as H. We will extend the perpendicular KH until it touches side MD. We define the touching point of the extended perpendicular KH and MD as T. Point H is the point of tendency of tangent TK with this circle. We join points O and H together by a straight line. OH is the radius of the circle that is equal to X. The radius OH is drawn to the point of tendency, that is to say it is drawn to point H, that is the point of tendency of tangent TK with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent TK will be perpendicular to the radius OH. So if TK is perpendicular to OH, it means that this angle equals to 90 degrees, and this angle it is also equals to 90 degrees according to rule number 1. So inside quadrilateral OH and K we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Angle MOH, this angle equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle MOH, it is equal to 180 degrees in its size. Any angle that is equal to 180 degrees must be a straight line. Therefore, MOH is a straight line. If MOH is a straight line, then MH is also a straight line. But line segment MH touches the circle at points M and H. And therefore, line segment MH is a chord that passes through the center of the circle, that is to say it passes through point O. Any chord that passes through the center of a circle must be the diameter of the circle. Therefore, MH must be the diameter of the circle. So I write it down. This MH is the diameter of the circle. Okay. In the next step, we'll focus on quadrilateral MHBK. In quadrilateral MHBK, we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral MHBK as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, MH must be equal to BK. So in rectangle MHBK, MH equals to BK. We can write here that MH equals to BK. And from this equation, BK equals to MH equals to the diameter, we will derive that BK is also the diameter of the circle. BK is the diameter of the circle. We know that the diameter of any circle is twice as long as the radius. But the radius of the circle equals to x, therefore the diameter must be equal to 2x. So the diameter BK equals to 2x in its length. You can write here that BK, this line segment BK, it is equal to 2x in its length. In the next step, we actually know that, found out that triangle, the right triangle TMK, the right triangle TMK is similar to the small right triangle AMB. Therefore, addition relationship exists between their sides. MK in the big triangle over TM, MK in the big triangle over MB in the small triangle equals to TM in the big triangle over AM in the small triangle. Repeat again. MK over MB equals to TM over AM. What is the length of MK? From the drawing, it is very easy to see that MK equals to MB plus BK. So MK equals to MB, that is 8 over 3, plus BK, that is 2x. So in total, MK equals to 8 over 3 plus 2x. Over MB is 8 over 3. And it is equal to TM. What is the length of TM? For the drawing, it is very easy to see that TM equals to TA plus AM. So TM equals to TA plus AM is 10 over 3. So in total, TM equals to TA plus 8 over 3. Over AM. AM is 10 over 3, so we substitute AM by 10 over 3. Okay, so we got this equation. Here we'll multiply 2x by 3 and then we'll divide it by 3 in order to overcome a factor with 8 over 3, and here also we'll multiply TA by 3 and then we'll divide by 3 in order to overcome a factor with 10 over 3. We'll do it now and we'll get that 8 plus 2x times 3 is 6x over 3 over 8 over 3 equals to TA times 3 is 3TA plus 10 over 3 over 10 over 3. So here we have 3 in the numerator, 3 in the denominator, so 3 get cancelled. Here also we have 3 in the numerator and 3 in the denominator, so 3 will also get cancelled. What is left for this equation after we cancel 3? So here we have 8 plus 6x over 8 equals to 3TA plus 10 over 8. Here we first multiply this equation and we get it 10 times 8 plus 6x times, and it is equal to 8 times 3TA plus 10. Here we'll open the brackets on both sides of the equation and we get that 8 times 8 is 80 plus 8 times 6x is 60x. That is equal to 3 times 8 times 3GA is 24GA plus 8 times 10 is 80. So here we have 80 on both sides of the equation, so 80 will get cancelled and we left only with 60x, that is equal to 24GA. Here we divide this equation by 24 and finally we get that GA equals to 60x over 24 is 2.5x. So in conclusion, found out that the GA equals to 2.5x. It's actually not GA but TA. Here it is TA. I accidentally wrote TA and GA instead of TA, so it is TA. TA equals to 2.5x. Here this is line segment TA. Is equal to 2.5x in its length. In the next step, I will copy quadrilateral ATBK in a new page. Actually, this is quadrilateral ATPA. This is a copy from the original drawing. This quadrilateral blocks a circle. This is the circle that the quadrilateral blocks. So I copy the circle that is blocked by the quadrilateral, the new drawing here. Okay. Actually, the quadrilateral and the circle touch each other at 4 points. That is to say, they are tangent to each other at 4 points. This is the first point that we define as M, the point of tendency between the quadrilateral and the circle. This is the second point that we define as N. The third point of tendency is here, that we define as K, and the fourth point of tendency between the quadrilateral and the circle is here, that we will define as L. So in the next step, I present to you rule number 2, and we implement rule number 2 in our drawing. So according to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule number 2, whenever you draw two tangents to a circle from a common external point, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. We can implement rule number 2 in our drawing. We'll focus on the common external point, point A. From the common external point, point A, we have two tangents to this circle. Tangent AN and tangent AM and tangent AM. And according to rule number 2, they are equal to each other. That is to say, AN equals to AM. So, if AM is A, then AN must be also equal to A. In the next step, we'll focus on the common external point, point B. Here. From the common external point, point B, we have two tangents to this circle. Tangent BN and tangent BK, and according to rule number 2, they are equal to each other. That is to say, BN equals to BK. So if BN is B, then BK must be also equal to B. In the next step, we'll focus on the common external point, point A. From the common external point, point A, we have two tangents to this circle. Tangent AK and tangent AN, and according to rule number 2, they are equal to each other. They must be equal to each other, so AK equals to AN. So, if AK is C, then AL must be also equal to C. And finally, we focus on the common external point, point T. from the common external point T, we have two tangents to this circle, tangent Tm and tangent Tl, and according to rule number 2, they are equal to each other. That is to say, Tm equals to Tl. So if Tm is D, then Tl must be also equal to D. Okay. So in the next step, we will add side AT to side BA in this quadrilateral ATGA. So what is the value of AT plus BA? From the drawing, it is very easy to see that the length of side AT equals to A plus D. So we substitute AT by A plus D. And BA, it's very easy to see that BA equals to B plus C. We substitute BA by B plus C. In conclusion, we found out that side AT plus side BA equals to A plus D plus B plus C. So we can change the order of the variables here. Instead of A plus D plus B plus C, we can write down that is equal to A plus B plus C plus D. We just change the order of those four variables. Okay. In the next step, we will add side side AB to side TA in this quadrilateral ATBG. So AB plus TA. From the drawing, it is very easy to see that the length of side AB of quadrilateral ATGA it is equal to A plus B. A plus B. And the length of side TA, it is C plus D. It is very easy to see that AT equals to C plus D. So in total, AB plus TA equals to A plus B plus C plus D, exactly as the value of AT plus BA. It is also equals to A plus B plus C plus D. So both those two expressions are equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AT plus BA equals to AB plus TA. Okay. What is the value of AT? AT equals to 2.5x. Therefore, we substitute AT by 2.5x. Plus BA or AB, it is the same. Is given as the equation that BA equals to 2, therefore we substitute BA by 2. we did AT plus BA equals to AB, A plus B plus C plus D, and AB so here we have two same letters for the two different points. That is AT plus BA equals to A plus B plus C plus D, and here it is AB plus DA that is equal to AP, A plus B plus C plus D. So here BA actually the quadrilateral is AT BK. I copied quadrilateral AT BK here, so it is AT BK. This point is point K and not point B. So actually we added points side AT to side BK. AT plus BK equals to A plus B plus C plus D. And here it is also AB plus TK. We actually found out that AT plus BK equals to AB plus TK. AT is 2.5x, BK, what is the length of BK from the drawing here? It is very easy to see that BK equals to 2x. So we substitute BK by 2x. And it is equal to AB. AB is 2, so we substitute AB by 2 plus TK. What is the length of TK from the drawing here? Here TK so actually we didn't calculate the value of TK. So we do it now. Because of the fact that the right triangle MTK is similar to the small right triangle MAB, we will derive that MT in the big triangle over MB in the small triangle is equal to TK in the big triangle over AB in the small triangle. Repeat again. mt over mb equals to tk over ab. What is the length of mt? When you go in this way, you need to see that mt equals to mb plus bt. That is to say, mt equals to mb, that is 8 over 3, plus bt, that is 2x. So in total, mt equals to 8 over 3 plus 2x over mb. mb is 8 over 3, and it is equal to tk. tk is unknown, so we leave it as it is, over ab. ab is 2, so we substitute ab by 2. So we can only find out that 8 over 3 plus 2x over 8 over 3 plus 2tk over 2. Here we multiply 2x by 3 and then we divide it by 3 in order to have a common factor of 8 over 3. And we get that 8 plus 2x times 3 is 6x over 3 over 8 over 3. It is equal to tk over 2. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled and we left only with 8 plus 6x over 8 equals to tk over 2. Here we cross multiply this equation and we get the 2 times 8 plus 6x equals to 8 times tk. Here we divide this equation by 2 and we get that 8 plus 6x equals to 4tk. Here we divide this equation by 4 and finally we get that tk equals to 8 over 4 is 2 plus 6x over 2 is 1.5x. So in conclusion, in total, we found out that tk equals to 2 plus 1.5x. Here, this line segment tk is equal to 2 plus 1.5x. So we return to our calculation that we did it here. So here AB is 2, and we just right now found out that tk equals to 2 plus 1.5x, so we substitute tk here by 2 plus 1.5x. In conclusion, we found out that 2.5x plus 2x equals to 2 plus 1.5x. So 2.5x plus 2x is 4.5x. And it is equal to 2 plus 2 is 4 plus 1.5x. Here we subtract 1.5x from this equation. And you get that 4.5x from minus 1.5x is 3x, that is equal to 4. Here we divide this equation by 3, and finally we get that x equals to 4 over 3 units. So the area of any circle, the square brackets is the sign for the area. It is equal to pi times the radius square. If r is the radius, it is pi r square. In our circle, the radius is x, so it is pi x square. So here we just right now found out that x is 4 over 3, so we substitute x by 4 over 3, so it is 4 over 3 square. So in conclusion, we found out that the area of the circle equals to pi 4 over 3 square. Pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, found out that the area of this circle equals to either 16 pi over 9 square units, so in terms of numbers, it is equal to 5.585 square units. So we finished to answer this question. In the next step, I will summarize the lecture. So in this lecture, we found out the area of this circle. So in the drawing we have quadrilateral ABCD. Inside this quadrilateral we have this circle. We know that side AB equals to 2 units in this length, side BC equals to side BC, they are both equal to 8 units. This angle DCB equals to 90 degrees, this angle ABC equals to 90 degrees also. And our mission is to find out the area of this circle. So first of all we did the construction. That is to say, we extended side DA and side CB until they touch each other. So this is their touching point. We define their touching point as point M. So here, side BC is one side of the quadrilateral, therefore it is absolutely a straight line. Then when we extended the straight line BC by straight line, the result is CM. That is also must be a straight line, because when you extend the straight line by straight line, the result must be a straight line. So CM is a straight line. If we focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle here must be equal to 90 degrees. So in triangle, the right triangle A and B, this angle equals to 90 degrees. We define this angle as theta. So theta plus 90 degrees. So here we have the missing angle. Here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right B triangle DMC, this angle equals to theta, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Then we proved that the big right triangle DMC is similar to the small right triangle A and B. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big right triangle DCM are correspondingly equal to all the three angles on the right triangle ABM. Therefore, those two right triangles are similar to each other according to angle similarity rule. What is angle similarity rule? Angle similarity rule is that if you prove that all the three angles in one triangle are correspondingly equal to all the three angles in another triangle, then the two triangles will be similar to each other according to angle similarity rule, exactly as we proved about those two right triangles. So, because of the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that MC in the big triangle over MB in the small triangle equals to DC in the big triangle over AB in the small triangle. Repeat again. We conclude that MC over MB equals to DC over AB. What is the length of MC? It is very easy to see from the drawing that MC equals to MB plus BC. That is to say, MC equals to MB plus BC. BC is 8, so in total MC equals to MB plus 8. So here we substitute MC by MB plus 8, so it is MC, it is MB plus 8 over MB equals to DC. DC is 8, AB is 2. 8 over 2 is 4. So MB plus 8 over MB equals to 4. We multiply this equation by MB and finally found out that MB plus 8 equals to 4MB. We subtracted MB from this equation and finally found out that 8 equals to 4MB minus MB is 3MB, so 8 equals to 3MB. We divided this equation by 3 and finally found out that MB equals to 8 over 3 units. And B equals to 8 over 3 units. Then we implemented the Pythagoras theorem on the right triangle A and B. According to the Pythagoras theorem, AM squared equals to AB squared plus BM squared. Repeat again. According to the Pythagoras theorem in the right triangle A and B, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, so AB squared is 2 squared, that is 4 plus MB squared. MB is 8 over 3, therefore MB squared it is 8 over 3 squared. So AM squared equals to 4 plus 8 over 3 squared, it is 8 squared, that is 64 over 3 squared, that is 9. Here we multiplied 4 by 9 and then we divided by 9 in order to account factor with 64 over 9. And we know that AM squared equals to 4 times 9 is 36. So in the numerator we have 36 plus 64 over 9. 36 plus 64, it is 100 over 9. We took out of this equation and finally found out that AM equals to the square root of 100 over 9. The square root of 100 is 10 and the square root of 9 is 3. So in total we found out that AM equals to 8 over 3 units. Here, the hypotenuse AM is equal to 8 over 3 units. Okay, then I presented to you rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, tangent to a circle is perpendicular to the radius drawn to its point of tendency. AB is tangent to the circle at point M. We have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. So we can implement rule number 2 in our drawing. we define the center of this circle as O. AB is tangent to this circle at point M. We join points O and M together by straight line. O is the center of the circle, M is the point of the circle itself, therefore OM is the radius that we define as X. The radius OM is drawn to point M, that is the point of tendency, therefore tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. BC is tangent to the circle at point N. We join points O and N. ON is the radius of the circle that we define as X. The radius ON is drawn to point N, that is the point of tendency of tangent BC with this circle, and therefore whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. In quadrilateral OMBN, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Then we draw perpendicular on BC, that is also tangent to this circle at point H. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. Edge is the point of tendency of tangent TK with this circle. We join points O and N together by a straight line. O and N together by a straight line. OH is the radius of the circle that is equal to X. The radius OH is drawn to point H, that is the point of tendency of tangent TH with this circle, and therefore whenever a radius that is drawn to the point of tendency, tangent TH will be perpendicular to the radius HO. If HT is perpendicular to HO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Quadrilateral HO and T, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 180 degrees, is equal to 360 degrees. So we have angle AOM, this angle AOM equals to 90 degrees plus 90 degrees, it is 180 degrees. Any angle that is equal to 180 degrees must be a straight line. So HM is a straight line, but HM touches the circle at point H and M. Therefore HM is a chord that passes for the center of the circle, that is to say passes for point O, that is the center of the circle. Any chord that passes for the center of the circle must be the diameter of the circle. Therefore HM is the diameter of the circle. Yeah. For HM is the diameter of the circle. Then we focus on quadrilateral MHBT. In quadrilateral MHBT we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a left angle if not a square. So quadrilateral, we will relate to quadrilateral MHBT is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say MH equals to BT. Okay, MH equals to BT. So we can write down that it is actually MH equals to BK. MH equals to BK. So we can write down that MH equals to BK. And from this equation, BK equals to MH equals to the diameter, we realize that BK is also the diameter of the circle. BK is the diameter of the circle. The diameter of any circle is twice as long as the radius. The radius is x, therefore the diameter BK is 2x. Yeah, the diameter BK equals to 2x in its length. We extended the perpendicular to the edge until it touches the circle, until it touches side DM. Define the touching point as point T. Then we proved that the right triangle TMK is similar to the right triangle ABM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta, that is a common angle, it belongs to both triangles, therefore angle theta equals to itself. And finally, here, in the right triangle TKM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. So those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually succeeded to prove that all the three angles of the right triangle TKM are correspondingly equal to all the three angles in the small right triangle ABM. Therefore, the two right triangles are similar to each other according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. That MT in the big triangle over MB in the small triangle equals to TK in the big triangle over AB in the small triangle. I repeat again. MT over MB equals to TK over AB. MT, from the drawing, it is very easy to see that MT is equals to MB plus BK. That is to say, MT equals to MB, that is 8 over 3, plus BK that is 2x. So in total, M is actually MK. It is actually MK here. So MK equals to 8 over 3 plus 2x. So actually MK equals to 8 over 3 plus 2x. MB equals to 8 over 3. TK is the missing side, and AB is 2. We multiplied 2x by 3 and then we divided by 3 in order to have a common factor with 8 over 3. So in the numerator we have 8 plus 2x times 3 is 6x over 3 over 8 over 3 equals to TK over 2. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled, and we left only with 8 plus 6x over 8 equals to TK over 2. We first multiplied this equation, we found out that 2 times 8 plus 6x equals to 8 TK. We divided this equation by 2 and finally found out that 8 plus 6x equals to 8 over 2 is 4, so it is 4 TK. 8 plus 6x equals to 4 TK. We divided this equation by 2 and finally found out that TK equals to 8 over 2 is 4 plus 6x over 2 is 1.5x. In total, we found out that TK equals to 2 plus 1.5x. So we can write down here that the length of line segment TK is 2 plus 1.5x. Because of the fact that the big triangle TKM is similar to the small triangle ABM, additional relationship exists between their sides. The relationship is as follows. MK in the big triangle over MB in the small triangle equals to TM in the big triangle over AM in the small triangle. Repeat again. MK over MB equals to TM over AM. what is the length of mk? From the moment it's very easy to see that mk equals to 8 over 3 plus 2x. mb is 8 over 3. Here we substitute mk by 8 over 3 plus 2x, and we substitute mb by 8 over 3, and it is equal to Tm. What is the length of Tm? From the domain it is very easy to see that Tm equals to Ta plus Am. That is to say, Tm equals to Ta plus Am, that is 10 over 3. So in total, Tm equals to Ta plus 8 over 3. So therefore, we substitute Tm by Ta plus 8 over 3, and Am is 8 over 3. So here, in this part of the equation, we multiply 2x by 3, and then we divide it by 3 in order to have a common factor with 8 over 3. And we got that 8 and 2x times 3 is 6x over 3 over 8 over 3 equals to, here we multiply Ta by 3, and then we divide it by 3 in order to have a common factor with 10 over 3. So we have here 10 plus 3 times Ta is 3Ta over 3 over 10 over 3. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And there also we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled here also. And we're left only with 8 plus 6x over 8, that is equal to 3Ta plus 10 over 10. Here we cross multiply this equation, and we found out that 10 times 8 plus 6x equals to 8 times 3Ta plus 10. 8 times 10 is 80, and 8 times 6x is 60x. 8 times 3Ta is 24 3Ta, and 8 times 10 is 80. We have 80 on both sides of the equation, so 80 will get cancelled, and we left only with 60x, that is equal to 24Ta. We divided this equation by 24. 60x over 24 is 2.5x. Therefore, in total, we found out that Ta equals to 2.5x. Here, this line segment Ta, it is equal to 2.5x. Then I copied the quadrilateral ATKB here in the new page. This is the quadrilateral ATBK that I copied from the original drawing. This quadrilateral ATBK blocks a circle. So I copied the circle here in the new drawing. Actually, the quadrilateral and the circle touch each other at 4 points. 1, 2, 3, 4. That is to say, they have 4 points of tangencies between them. M, N, K, and L. Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, whenever you draw two tangents from a common external point to a circle, from a common external point to the circle, then the lengths of those two tangents must be equal to each other. In this case, PA equals to PB. We implemented rule number 2 in our drawing. In our drawing, we have the common external point, point A. From the common external point, point A, we have two tangents to this circle, tangent AM and tangent AN. And according to rule number 2, AM must be equal to AN. So if AM is A, then AN also must be equal to A. Then we focus on the common external point, point B. From the common external point, point B, we have two tangents to the circle, tangent BN and tangent BK. And according to rule number 2, they must be equal to each other. That is to say, BN equals to BK. Then we focus on the common external point, point K. From the common external point, point K, we have two tangents to this circle, tangent KL and tangent K. This tangent and according to rule number 2, they must be equal to each other. That is to say, KL equals to this tangent. Okay. And finally, we have the common external point T. For the common external point T, we have two tangents to the circle, tangent TM and tangent TL. And according to rule number 2, TM equals to TL, so if TL is D, then TM must be also equal to D. Then we added for side AT to side BK in quadrilateral ATBK. ATBK. AT equals to A plus D and BK equals to B plus C. In total, AT plus BK equals to A plus D plus B plus C. You can change the order of the variables. Instead of A plus D plus B plus C, you can write down A plus B plus C plus D. Then we added side AB to side TK in this quadrilateral AT BK. AB is A plus B and TK is C plus D. So in total, AT plus TK equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they must be equal to each other. That is to say, AT plus BK must be equal to AB plus TK. AT equals to 2.5x, therefore we substitute AT here by 2.5x. BK equals to 2x, therefore we substitute in our equation BK by 2x. AB equals to 2, so we substitute AB by 2, and finally TK equals to 2 plus 1.5x, therefore we substitute TK by 2 plus 1.5x. And finally we found out that 2.5x plus 2x equals to 2 plus 1.5x. 2.5x plus 2x is 4.5x, 2 plus 2 is 4 plus 1.5x. Then we subtracted 1.5x from this equation and finally found out that 4.5x minus 1.5x is 3x and 3x equals to 4. Here we divided this equation by 3 and finally found out that x equals to 4 over 3. That is to say the radius of this circle equals to 4 over 3 units. The area of any circle, this is the sign of the area, the square brackets. So the area of any circle equals to pi times the radius squared. If the radius is r, it is pi r squared. In our specific circle, we define the radius as x, therefore the area will be equal to pi x squared. X, we just right now found out that x is 4 over 3, so we substitute x by 4 over 3. So the area of our circle will be equal to pi times 4 over 3 squared. Pi times 4 over 3 squared equals to pi times 4 over 3 squared is 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, found out that the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.